Right. Okay. So the step one, we got to draw the picture, right, and this parameterize this path because we're computing a scalar line integral, and scalar line integrals are always computed based on the parameterization. So here's our picture. Something like this, and let's see. The spring is axis is the z-axis. The bottom's resting on the xy plane at the point 2, 0, 0, and then it goes and takes 7 turns to get up to this height, which was, I already forgot. What's the height? 10 inches tall. All right, so I'm going to take a whack at drawing this. It's going to be a bad drawing, but it'll be good enough. Something like that. Bad. My apologies for the bad art. Does everybody see roughly? And I think I only made 6 turns. Let's see here. 1, 2, 3, 4, 5. Yeah, so I blew it. 6 turns. My apologies. Yeah.
I just think it's unclear from the question which direction that initial direction vector from the base point is moving. Just.
Okay, so it says here moving counterclockwise as seen from above when moving up the spring. So in other words, if you're moving, so this is up the spring, right? And as you're moving up the spring, it says counterclockwise as seen from above. So that means it has to go like that.
I mean, you could still move like in the direction of the vector 0, 1, and still initially, and then move counterclockwise, right?
I'm not following.
So I mean, the kind of the center of the base of that spring could be, as I saw it, anywhere in a circle.
Well, no, it says that it's the axis of the spring is the z-axis. That's in the sort of at the beginning of the third line. It said it is oriented with its axis on the z-axis.
Okay. Okay.
Yeah. So in other words, that's got to be the center axis of the spring. And it starts there, and the radius is 2, and counterclockwise as seen from above, going up, etc.
Okay.
Does that make sense?
Yeah.
No, you're definitely right that it's confusing. Yeah, because there's just so much words that goes into it. But if you just break it down one little bit at a time, I claim that this is the only. Yeah, right. Okay. All right. So now, for step 1, let's just parameterize this, just so we can have that done, and everything else is just further details. So. Now, we've parameterized helixes before, right? And so we know that specifically the idea is that a helix is such that when you project it down into the xy plane, it's just going around in a circle. And this is a circle of radius 2, so I guess we could parameterize this with something like, let's have x, y. We'll worry about z in a second. But we could have sine and cosine. We'll worry about what to put in there in a second. And we know that as the projection is going around in a circle down here in the xy plane, the z-coordinate is just going to be increasing at a constant rate. And that means that z is going to be just some constant times t. And we just want to rig up these constants. Let's see, this is something times. Huh? I'm sorry?
Why are you using x cosine?
So because I'm starting here. In other words, if I look at the projection down to the xy plane of as I go up the spring, the projection in the xy plane is just going around in a circle in the xy plane, and in particular, it's a circle where I start here on the x-axis. Oh, I'm sorry, I forgot a factor of 2. Sorry about that. Yeah. So was that the okay? So 2 cosine whatever and 2 sine whatever because we're going around in the circle of radius 2. Is that cool? All right, now I need to get up to height 10, and in the amount of time that it takes me to get to height 10, I need to go up. I need to go around 7 times. So there's different ways that you can do this. I'm tempted to say I like it when t. I want to just let's just have these be 1 in here. Let's just have t represent the number of thetas that I go around, the number of angles the number of radians that I go around the z-axis. So let's just say cosine t and sine t. So now if this is going to if this is actually going to go around 7 times, then with this choice, t has to go from 0 to 14 pi. That goes around 7 times. Cool? Is that okay? Everybody good? Yes.
Where did you get the factor of 2?
Where did I get the factor of 2? So the circle has radius 2. So if I just did sine and cosine, that would go around a little circle of radius 1.
Oh.
Yeah. Said differently, since the projection is a circle of radius 2, the equation is r equals 2. Right? And if you take this r equals 2 and plug that into x equals r cosine theta and y equals r sine theta, well, if r is 2, then you get 2 cosine theta and 2 sine theta. Does that make sense? Okay. All right. Okay, so all right, I've got it to where it definitely now goes around 7 times with radius 2. And now the big question is, well, yeah, but I need to make sure that in that amount of time, it needs to make it up to height 10 exactly. So, well, if t goes from 0 to 14 pi, I need to sort of multiply by 10 over 14 pi here, so that when t is equal to 0, it's at height z equals 0. But now when t gets to the end at 14 pi, I need that to actually end up being 10. Does that make sense? So we're taking the helix. I think we did an example of a helix somewhere in chapter 2 probably, or yeah, it must have been chapter 2.
In cross section.
I'm sorry?
I think we did in the section of cross section.
Is that right? Okay. So all this is a modified version of that, right? I'm taking that parameterization and just kind of bending and twisting it as necessary. Got to stretch it out to give it a radius of 2 and squish it down or as necessary to make it go around 7 times between height 0 and 10. That kind of thing. So pause again to make sure everybody's comfortable with my parameterization. Okay. All right, so now with that being done, I want to compute, the problem says compute the volume of rust on the spring. Now, I claim that this is going to be a scalar line integral. That's no surprise because a section on scalar line integrals. But in particular, now I'm going to draw a bit of spring here. Here's a cross section of the bit of spring, and here's that spring kind of rolling around like this, and it's, off it goes. But there's an accumulation of rust on it that's going to sort of be like this layer around the outside. And that's going to go along. Right, so this accumulation of rust, it goes all the way along the coil, but I just want to talk about some little bit here. Specifically, I want to talk about how much rust has accumulated over a length ds of the curve. Does that make sense? Okay. Yeah, question?
From the wording of the question, it seems like the wire making the spring is covered with something else because the wire has a smaller radius.
The wire, yeah.
The spring. So what is the rest of the material covering the wire?
Maybe I'm not quite understanding your question. So the radius of the wire itself is a 1/10 of an inch.
Yeah.
Right. So this has got a real tiny little radius here. 1/10. And the thickness, so that thickness of the rust is given by this thickness function. That's this t of x, y, z function. So I'm not quite understanding.
What is the 2-inch radius of the spring?
That's the 2-inch radius of the coil. That's the radius around. That's this thing here. Oh, I'm sorry. Yeah, here we go. It's this radius. Like that distance is 2. Does that make sense? Okay. Okay. All right. So now, keep in mind the way we do scalar line integrals is the whole idea is that depending on what the application, whatever the application is, we've got to find some way. We're going to chop up the curve into little pieces. So we've got this this curve defining sort of the center of the wire as it moves along. I'm chopping up that little bit of curve into little pieces, and on each piece I want to figure out how much stuff, whatever it is that I'm adding up, how much stuff can I associate to that little bit of the curve. So at this point, I've got a picture here of what my rust accumulation is on that little piece of curve. The corresponding rust accumulation is this. It looks like a ring. Right? Everybody see the ring? Looks like this. Right? And how do you compute the amount of rust there? Well, I mean, this, you got a little geometry problem. We have, you could sort of like slice it on that edge, and it's going to roughly open up to being a little rectangular box. And that dimension is that t function. This dimension here is the circumference of that circle. Well, what's the circle? The circumference is 2 pi r. R is a tenth. So this is 2 pi over 10, that distance. And this height looking thing here, that's this ds. So this little ring of rust, how much volume of rust do you have? Well, the volume of rust is the product of these three things. It's 2 pi over 10 times t times ds. Let me pause for a second before I go on. And how are we doing on that? Does everybody believe that? Yeah. Oh, he's thinking. All right, so let's question. Anybody? Okay, let me wrap it up, and if you have a question, feel free to jump in. So the whole idea is we're adding up. We want to know the total amount of. We've got the little bits of rust that look like this are accumulating over the entire wire, right, going all the way around. So let's call that the total curve C. So altogether, the total amount of rust, the total volume of rust, is we're going to add up over the entire curve these little slices of rust. Yeah, question.
So the way I'm understanding this is that we're assuming that for some small ds, the dimension t is in fact constant around the wire.
Yeah, that's right. And you can confirm that because if you look at this formula over here, this formula for t, you can see it's a continuous function. Right. Oh yeah, no, I see what you're saying. Yeah, around the wire. We're taking that approximation. In other words, we're evaluating the thickness. Even though the thickness is over here, we're evaluating there. It's just a little bit off. So there's an approximation going on here.
Okay,
yeah.
So in reality, that would affect.
Yeah, and in reality, it'd be just a little bit different from what we're writing down here. So this is a very close approximation. Notice, by the way, that the thickness here is very small. It's going to be it involves y and z, sure, but then divided by 1,000.
Okay.
So we're talking about really thin little layers here of volume. And furthermore, the thing itself, the wire itself, is 1/10 of an inch thick. So that's not quite as micro, but it's still pretty small. And but yeah, you're right. This is an approximation.
Okay.
Yeah, absolutely. Okay, so let's write this down. So integral over the curve of this little formula that we have for the amount of rust on that little bit of curve, and so that becomes an integral over the curve. 2 pi over 10, of course, is pi over 5. Let's pull that out. And we have that. And we have a parameterization of this curve. And so this is just a plug and chug problem at this point. You've got to take your parameterization. So you can rewrite this as pi over 5. Let's see here. We're going to have t of your parameterization, which is 2 cosine t, comma 2 sine t, comma, and then let's see, 10 over 14 pi is 5 over 7 pi. T. There's your x, your y, and your z that you plug into the t function. ds, of course, is the length of x prime dt. So you've got to take your parameterization, compute x prime, compute the length, etc. And this is an integral that you can work out. Is that okay? It make sense? You don't look happy.
So
Just absorbing? Okay. All right. All right. So yeah, this is in some sense, there are two parts to this problem that are hard. I mean, on the one hand, what you might call the phase one part of the problem, where you look at a bit of the curve and you try to take the problem as a whole and write it as an integral. I mean, this getting from here to here involves this picture and how you break down the rust and view it as a product with ds. So the phase one part of the problem is tricky and geometric and little confusing. Then the phase two part of the problem, turning this into a dt integral. Oh, sorry, here we go. dt integral, by the way, this is from 0 to 14 pi. Is also hard because you have to parameterize the curve, and the parameterization is, a little tricky. You've got to kind of adapt something that was done in the book to this slightly different circumstance. So it's got two parts of this problem are tricky. Yeah, absolutely.
Can you move down the last section?
Oh yeah, sure. Yeah, this part here. Yeah, and then let me just say ... That's something that's got to be evaluated. Okay, is everybody good? All right, let me go ahead and stop this. Oh, yeah, question? Oh, okay, hang on.